This is the BBC micro power supply, and I'm going to replace a certain number of the capacitors here. It's a bit difficult to see, but if you look down here, this guy over here, this film capacitor right in there, just where the input power comes in, is blown. Okay, that's a class X capacitor. If you hang on to the end of the video, I'll explain a bit more about these things and how they function. But that's the main thing that we have to replace, and some of these friends back there as well. With time, unfortunately, capacitors don't last. So one often needs to replace old capacitors in these kind of projects. High voltage danger. This is important. Obviously, everyone knows that when this is plugged in, it would be exceptionally dangerous. There would be a decent chance of loss of life, even, if you muck around with this. Now, what people don't know, here there's kind of this caution at the back here. No user serviceable parts. What they're trying to say is people who don't know what they're doing shouldn't really mess around with this. The reason being is that these capacitors, these guys over here, now, capacitors act as battery stores. It's very possible that these still hold charge, and they can be exceptionally dangerous. I have actually been shocked by a 350 volt capacitor, probably something this size, and it was only partially charged at the time, and it was probably the worst shock I've ever gotten. And that includes mains current shocks, which were nothing compared to the pain that I felt from that particular shock. Now, that was also just on one finger, where I must have touched the terminals by mistake. And if you imagine you touch those across your body, that could be fatal, depending on how much energy is in those capacitors. It's probably okay. These capacitors are probably discharged. I left this plugged in to the motherboard after disconnecting the mains, meaning that the energy should have dissipated into that and be used, but it's impossible to know. So I'm going to be very careful when opening this up. I've got these rubber gloves to give me some protection. They're not electric rated at all. There's only a very small rubber coating here, but it should provide some level of protection. So I'm going to go ahead, take the chassis off, which is actually protective, and let's see how we go. Okay. Wow, that was much harder to get out than expected. Imagine I've freed out this part of it. It's kind of almost necessary to take this out fully. Victory! Okay, I've got this guy out of there. Hope we didn't damage him too much. Okay, good enough. See the board here, all the electrolytics, film capacitors, and the electrolytics are out. Ceramics don't need replacement. So we're going to start by replacing the class 2 film capacitors. This is the 100 nanofarad one. And what we're going to do here is we're going to reuse some of the solder, and where it's not sufficient, we're going to add some solder over there. There we go. Nice. Okay, what you want to do with this is you want to actually heat up the pad and not the and not the leg itself. Okay, I didn't do a great job of that, but when it heats up the pad, you get a much better connection. Because we're dealing with the power supply, I thought I'd digress and try explain some of the operation of that power supply and how it works in a very high level for those interested. So there are a number of features to a power supply, but the main aim of this block of electronics is to convert from AC power, which is our mains power, to DC power, which is the direct current that is needed for the electronics to function. And AC power over here, running at say 250 volts AC, 50 hertz is the frequency, looks something like this. So the frequency refers to the period of the AC sine wave. So if I can draw a quick graph over here, we would say that you have this sine wave, that's our AC power, and this is a function of time and voltage. Voltage changes over time, so it switches forwards and backwards. It starts positive, 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 goes down to 0, switches negative, 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 forwards and backwards. So you have this alternating current. But we need to get it to a state where we've got this, over time, stable direct current over here. That's your voltage. Some voltage, let's say 12 volts from 250 volts AC. So how do we do that? There are a number of ways to do this and different types of circuits. But generally, a transformer is used. A transformer is something that we draw a symbol like this. Sorry, I've never been really good at drawing transformer symbols. And this is kind of the first stage, because we need to get from this high voltage, relatively high voltage, to a low voltage. So what the transformer allows us to do is to convert from the high voltage to the low voltage. And without getting into too much detail, there is a core, say an iron core, a ferrous core. Okay, so you can have this block of iron, and you have windings, basically a wire that is wound around this side, and another one that is wound around the other side. And here you give it your AC current, right? So you've got your AC going in here, and this is your AC coming out. And the voltage level of that coming out is a ratio between the number of windings on the input side and the number of windings on the output side. So this is called the primary coil, and this is called the secondary coil. So this is NP, the number of windings on the primary, ratio to the number of windings on the secondary coil. So you can work out the ratio and how many times you have to wind around in order to convert from 250 volts AC until let's say around 12 volts AC. This is what's called RMS current. We're not going to go into that too much. You can look it up in your own time. You could think of it more like 17 volts AC. Okay, but we're not going to go into detail with what that is. So this is stage one. We've taken our 250 volt AC current, and we've now have 17 volts AC current. So the next thing we need to do is convert it to DC current. Again, numerous ways of doing it, but the circuit we use here is called a rectifier circuit. Rectifier. And the basic rectifier can be made with 4 passive components, 4 diodes, right? So this component is a diode. Now, the main property of a diode is that in forward bias, it conducts current when it's connected in the right polarity. Let's think about it that way, without speaking about breakdown. And in reverse bias, i.e. you've turned it the wrong way around in the circuit, it doesn't conduct at all. So how this rectifier helps us is as follows. So again, to recap, at this stage we have this wonderful AC current going up and down, and it's going forwards and backwards, positive and negative, but it's now at 17 volts. And we want to convert this positive-negative swing to a positive current. That's our aim over here. So the rectifier is going to allow us to go from that to this type of picture. So in the positive half of the period, we're going to go up, positive. And then when we would be negative, we're going to go positive again. Okay, and then you're going to get this, and so on and so forth. You're going to keep going. So it's kind of like a noisy DC current, right? A noisy positive current. And how it works is as follows. So with the diodes, we can construct a circuit like this. So we've got our transformer over here. Let's draw my transformer. I'm a terrible drawing of one. That's going to do our step down transformation, stepping down from that voltage to that voltage. And then we're going to connect this bridge rectifier circuit that I'm going to build here with diodes. And it's going to look something like this. Sorry, I really haven't given myself much space to draw it here. Okay, it's going to look like this. It's weird. It's going to look like this strange drawing over here. Wow, I've done a really bad job. Oops, sorry, this has to be facing this way. Apologies. This diode is facing that way. Yes, okay. So we can label these as like diode 1, diode 2, diode 3, and diode 4. And this is going to be connected to the 2 points over here. And our current, our output here, V out, that's this thing, V out, is going to be connected to over here. That's V out. Now how it works is when the current comes in, when we're in the positive upswing, right, that's the current, so the potential difference, yeah, that's positive and that's negative on this first half, then diodes 2 and 4 are going to conduct, and when it swings out the other way around, diodes 1 and 3 are going to conduct. And this basically means that no matter which pair of diodes are conducting at any one time, the V out is always going to be positive. Because if it's swinging to the negative, you just got the other 2 conducting and going on. It takes a little while to get one's head around this, and you can look at it offline if you're interested in knowing further. But that's a basic operation. So stage 1, we've done a step down transformation from 250 volt AC to 17 volt AC. Stage 2, we've rectified it through a rectifier circuit, a bridge rectifier in this case, and made it all positive. And the next thing we need to do is switch from this noisy positive 17 volt to a smooth DC current. So this is what we have going in. Let's go there, draw that again. 1, 2, 3. Draw a few more of these. 4, sorry, not to scale. 17 volt. And what we want out of this step is to be left with a wonderful smooth, say, I don't know, 12 volt DC current. And how this works is we need a filter. And I'm not going to go into too much detail about the construction of this filter. I'm just going to kind of in a high level mention capacitors and how they work. And after this, I'm going to digress to capacitors and their operation, because it's actually important for understanding a lot of parts of this power supply. But for now, we're just going to draw our filter as kind of this black box. I'll call it right here, filter. Filter. And we take our noisy signal in. 2, 3, 4. And out comes our DC. Now, how that works mostly is that we have a capacitor inside. Okay, this is a symbol for capacitor. In terms of DC current, if you're drawing a DC circuit, you can almost think of a capacitor as a as an open circuit. So if so that's my little battery. I'm going to draw you a DC circuit with a resistor here. Okay. Now, if we had a capacitor over here in series, there wouldn't necessarily be any current flowing in that in terms of DC. Okay, you can consider it as if that circuit is open. That's why if you, and we'll get into more why this is actually a positive property, right? And what capacitor actually does and what capacitance is, because naturally it's not just an open circuit, right? Otherwise we wouldn't use them. But you can connect them in like a configuration like this. Say you have a positive 5 volt and ground. If you connected a circuit, if you added a capacitor into that circuit from the line to the ground, that wouldn't short circuit the circuit at all. And again, I'll digress and I'll tell you exactly what this would do in terms of the circuit in a little bit. But for now, all we've got to think about is a capacitor and how it works. And a capacitor in its basic form can be thought of as a battery store that's able to be charged. And how it works in this filter, if you imagine here, when we're on the upward swing of this curve, right, when voltage is going from 0 to the peak, we are charging the capacitor. Electricity is flowing in to this capacitor, charge is flowing in and it's charging up, okay? So as we go up there, the capacitor charges up. It's nice and charged when it hits there. Right, you pick a value that can hold sufficient charge, right, that it's not less than the value that you need, right, to come up. And then when we're on the downward swing, when we're going from peak to 0, because the energy, the potential is dropping on the input side here, right? This is the voltage input, 17, and this is our voltage output, our lovely filtered voltage. As it's going down, the charge is flowing out of this capacitor. And if you've ever been in a Toyota Prius and you've seen that great visualization of, the electric motor, they have this little motor thing, and when you regeneratively brake, you can see the little charge flowing in, and then when you're driving off with your electric motor, you can see this charge flowing out. They've got a little visualization. It's a similar thing to that, right? Sorry, I've drawn a motor symbol, but really I meant this is a battery. Okay, it's just a battery, and that charges up and then flows out to the motor when it's needed. It's the same thing here. So as we're on the upward peak, as I say, energy flows in, charges it up, going down to 0, it flows out. And this all works in one go together. So what you are left with at this end of the process, you can imagine this is a graph. We are charged. Our battery is charged at time 0, right? Okay, our battery is charged. And we're still going up. Sorry, our battery is charging. But as it goes up, right, we've got this type of graph. Okay, this is the voltage. And as it drops, the capacitor is making up for that gap, for this gap over here. So it continues. And it charges up again. There's no problem. There's enough energy. We keep going out. And then it's making up for that gap. And then charging up, but it's making up for the gap. And what's really happening, so what you're left with is DC current. 12 volt DC current. What it actually looks like, unfortunately, is more of a noisy signal. There's kind of this ripple ripple over here because of the AC current, right? It's never going to be perfectly smooth yet. And whether this ripple is okay, is tolerable for your application, depends on what is consuming the energy on the other hand. For example, a battery charger wouldn't care, right? If you're just charging up some 1.5 volt batteries, it doesn't really care about that because it goes up and down. But for sensitive electronics, this is going to be a bad news to introduce noise into the system. And this is going to need to be filtered out further. And that's when we discuss with capacitors, we're going to see when the circuit can assist us with this ripple as well. So this is the basic operation of this conversion from 250 volt AC to some value, in our case maybe 12 volt DC. First we have this transformer that steps down from the higher voltage to the lower voltage. Then we have a rectifier that basically rectifies the negative voltage and turns that half period into a positive voltage. And then we have a filter that smooths it out into a wonderful DC voltage current for us. And that filter includes the magic component called a capacitor. I'd like for a moment to speak about our friend the capacitor. A capacitor can be thought simply of as an energy store or a battery. So this is the symbol for the capacitor. And it's defined by the following function. Current over time is proportional to the capacitance value, and the rate of change, okay, so it's of voltage over time, okay, it's dV over dt. So you can imagine a graph like this. You could imagine that as the capacitor charges up, so it's charges, reaches a point, and then that would kind of be its saturation or its fully charged state, and then it would discharge like that. Then you would have a charge it up again, and then discharge. And different types of capacitors have different functions, or their charge rate and their discharge rate and how much energy they hold. It's all a bit different. We're not going to go into those distinctions right now. There's a lot of different variations to choose from. But just to mention three different types of capacitor. The first one's called a film capacitor. Second one is electrolytic. And third one is a ceramic. Let's take a look. Electrolytic capacitor basically looks like these guys. Could be aluminium electrolytic capacitors, and they have to be connected to a circuit in a certain way. So the polarity, the cathode, is the little leg that's connected to the negative side, and the anode is the leg that's connected to the positive side. The cathode is kind of marked by this black line. In these you can see the direction, okay, of the current. Here you would see ones that are kind of have these two-leg configuration, and this side would be the cathode. And these have to be connected in a certain polarity. In terms of the film and the film and the ceramic capacitors, you can connect them in any polarity, either way, and they'll work fine. So these little ceramic guys, it would work, or these, however you connected them, that would work as well. So why are we speaking about them? Each one of these kind of type of capacitors has different characteristics, and they're used for different things. Again, we're not going to go into too much detail. But it's worth mentioning that the film capacitor is very important for power applications, especially AC power applications. They're generally very tolerant to flame and kind of flame tolerant, right? So if you think back to our transformer / rectifier circuit, basically the AC to DC conversion that we just spoke about. And you can imagine that our power supply in the BBC Micro kind of has these three sections to it. So the middle bit is this AC to DC, which has got this, and we'll draw my little transformer. Draw our transformer over there. And that, as we mentioned, is responsible for stepping down the AC current from 250 volts to something a bit more reasonable, like 17 volts. And then it will be connected to a rectifier, like a bridge rectifier. You remember with those diodes. I won't draw the diodes here. But there's a rectifier circle that kind of transforms it into this positive current, but it's still kind of with a upward and downward cycle to it. And then it will connect to a filter. And we mentioned within that filter is going to be a capacitor, or series of them. And that kind of smooths out that. So we had, at this stage, we have this kind of all positive but cyclic kind of waveform for the voltage. And the filter will smooth it out to something more approximating what we can think of as DC. And sometimes it's a bit noisy over there. So that will kind of be this middle part that we spoke about. Now, on this side of it, especially in the BBC Micro, you can imagine that perhaps something like 12 volt DC current kind of enters this little section. But the BBC Micro might require a series of voltages, say 12 volt or 5 volt or even negative 5 volt DC current. So here you can imagine that you would have a bunch of regulators to convert from 12 volt DC to 5 or negative 5, or kind of use maybe operational amplifier to switch the current around. The regulator would probably, if we draw it as a black box, we won't go into how exactly it works. There are different ways of doing it. A very simple way of kind of stepping down the voltage DC would be to use a resistor divider circuit. Something like this, where you would have two resistors, and this would say be your 12 volts input, and this would be 0 volt. And over at this point, depending on the values of these two resistance, you could get a certain voltage like 5 volt. The problem with this type of circuit is that you're going to be connecting something to this 5 volt over here, and it's going to have some sort of resistance, most probably. It's called the load. You'd add some sort of load onto it. And because you've added this load in parallel here, you've actually changed the amount of resistance in this part of the circuit. So it means it's kind of changed the function over here, in which case you might not necessarily get the 5 volt you were expecting. But if you just cheaply need to, something that has a resistance that's not going to impact very much, and you can also select values for these that aren't impacted as much by whatever load you're adding, you can kind of have a poor man's circuit over here. But in any event, that's a digression. If we go back to our bit over here, you'll have this regulator that will produce, say, 5 volt from the 12 volt that's coming in. And it will do something, and we'll get into how capacitors can help us on this side as well. And then on the other side, the input side, this is the AC side. This is what goes to your wall socket. You can imagine this is your two lines, your live and neutral line, and you might even have a earth ground line, some sort of earth ground line. Ground. So sometimes what happens, you would imagine that in order to get into this path, AC to DC converter, you would like a clean sine wave, right? You'd like your power to kind of look something like that. In reality, there's interference. There might be other applications or other appliances on the lines in your house or from the power supply itself. There are many different things connected to all your plug sockets. In reality, this waveform looks a bit like this. It's kind of like spikes. It's not, in other words, it's not the clearest signal. And these spikes can be caused by electromagnetic interference, for example. And what we want to do, they can wreak havoc with the functioning on kind of the right-hand side here. So what you want to do before you hit the AC to DC part of the circuit, you want to get rid of these EMI frequencies, electromagnetic frequencies. And you do something called EMI suppression. Suppression. Hope I spelled that right. And one of the ways you can do it is by connecting a capacitor across your live to neutral lines. So you might add a capacitor here. Now we'll go a bit more into depth about this. This is called a line to line configuration. So let's draw out our live and a neutral again, and a capacitor across it. This is a line to line configuration. And the reason we do this is that if you can imagine the current or the waveform of the signal coming in, now as it comes in, on the upward cycle it's going to charge up the capacitor. On the downward cycle the capacitor is going to discharge very slightly, and basically depending on the value you select here, you can smooth out this waveform by filtering all these kind of frequencies. And it's called EMI. It's a configuration that allows you to suppress the EMI, electromagnetic interference, on an AC line. And the capacitor used here is the film capacitor variety, because it's got to be it's connected to the AC current, and there are a number of properties of this. And this particular capacitor, so basically these come in different classes, and the two main ones are class X capacitors and class Y. Yeah, those are basically the two classes. A class X capacitor is a capacitor that fails short. I'll explain in a moment what that means. That fails short, and class Y fails open. Now, what fail short basically means is that if something goes wrong, there's some overcurrent or some great surge or something's wrong with the capacitor, like I had when I plugged it in, my magic smoke came out of this. It blew up this part. What you want to happen is that you actually want the circuit over here that we had, the live and the neutral, you want it to short circuit. Fail short, meaning if the capacitor fails, you want it to act as if it's a short circuit, as there's a wire here. Now that's counterintuitive. You say, hey, why am I short circuiting my AC current? The reason is that you might have some component here, like a fuse, for example. So when this shorts out, the current spikes up and is going to burn out your fuse over here and disconnect it. You're going to disconnect your BBC micro from the mains, in essence. So your risk of shock goes down, and you stay alive if it fails short. Okay, so that's the idea behind these things. Keep you alive, right? If this failed open, you would have this live wire connected to this whole thing here floating, and risk of shock. If you touch something or something goes wrong, then not good news for you. Now, class Y, we'll digress slightly. In the BBC micro power supply, the class X capacitors here. But class Y can also be used, is used basically in this configuration, where we have live and neutral. These guys go in, and you have your ground. Between the class Y capacitors are placed between neutral and ground. So this is kind of class X. Let's just make sure we've got an arrow to it. And class Y is going to be placed in this configuration. Now, it fails open, meaning this thing blows up as if it's an open circuit between there. Why? Because your neutral and your ground and your live here, you don't want to short circuit your neutral to your ground, because whatever the ground's doing, whatever protection it's giving in this part of the circuit, it's kind of a similar reason to why you don't want a floating live. You don't want to disconnect the ground from the rest of the circuit. If you short out the neutral and the ground, you've in essence disconnected the ground from the rest of the circuit. So again, the idea is to keep you happy and alive. But in the BBC micro, basically we have these film capacitors that are in a line-to-line configuration instead of a line-to-ground configuration. So that's what that's called. In this configuration, it provides EMI suppression, electromagnetic interference suppression. That's all really I'm going to mention about the capacitors on this this part of the circuit. There's obviously a lot more to mention there, but we're just going to touch on the topic. Let me speak a little about the capacitors on the DC side of the circuit. Now, I mentioned you might pass the 12 volt through a regulator to get down to 5 volts. What happens is that this signal over here, as I mentioned, isn't necessarily the cleanest signal, or there may be other things in the circuit that are adding interference onto that line. And even the inner workings of the regulator might not produce the absolute stable 5-volt signal that you want to power your electronics. It might at times dip below 5 volts, go to 4.998 or even further, depending on what's happening here. So what we do is we can create a circuit with a capacitor. So you connect the regulator would be connected to ground, or 0 volts anyway. And if we add a capacitor on this output line over here, just like that, this thing is called a bypass capacitor. Let me write that. This is a bypass or a decoupling. Okay, or decoupling capacitor. What it basically does is smooths out the current that goes there. Because if you can imagine it, in regular operation, across here, this capacitor is charging up until it reaches 5 volts, right? Because that's what it's going to go. It's going to charge up and up and up and up. Now, if this input, well, this side here drops slightly, potential energy drops, the voltage drops, the battery still, the capacitor can provide the remaining, kind of smooth it out to keep it at 5 volts. Because in essence, it's a 5-volt battery, right? When it's charged up, it's a 5-volt battery. So if this drops a little, well, you've got 5 volts over here. It basically turns a noisy DC signal into kind of a nice flat DC signal. It's never going to be perfect, and you have to select the values, relevant values for these. Sometimes you need more than one, depending on what's happening on the rest of the circuit, but you pretty much can get this nice and smooth. Now, there's usually a capacitor on this side as well, but we're not going to go into that too. If you select the values correctly, I mean, it's for a very similar reason, obviously, to this side. And if you select the values correctly, you can get a very nice, stable signal. So that is called a bypass circuit, or bypass capacitor over here, from 5 volt to ground. If we look at these things, we can hopefully get a basic understanding of how our capacitors can help in terms of smoothing these signals. First, on the AC side, to filter out the EMI interference, electromagnetic interference, and also on the DC side to make sure that the power provided to the electronics that are pretty sensitive is as flat and as stable as possible.